Welcome to the AP Statistics Unit 4 Summary Review video, Part 2. I'm Michael Princhak, and I can't wait to explain everything in this video to you. Hopefully by now you've already watched Part 1 over basic probability. This is Part 2, and then don't forget to catch Part 3 over the binomial and geometric distributions. Alright, this video is all about random variables. What are they? How can we build probability distributions based on them? How do we find the mean and standard deviation of a random variable? And lastly, how to transform and combine random variables. So let's get right to it. Now, if a random process has outcomes of numerical values and those numerical values are uncertain, then we call it a random variable. Now, just know this, the outcomes of a random variable must be numerical values. Don't overcomplicate this. Just like in algebra class, a variable is a number that you don't know yet. Well, it's the same thing for a random variable. A random variable has an outcome that is a number that we just don't know what it is, but it could possibly be multiple different things based on uncertainty through that chance process. Now, there are two different types of random variables. Continuous random variables, which we'll talk about in Unit 5, so not right now, and discrete random variables, which we're going to talk about right now in Unit 4. Now, a discrete random variable is a variable that can take on a countable number of values. Each of those values of a random variable has a probability associated with it. And if you add up all those probabilities, you will get a sum of 1. Now, we typically use capital Latin letters like A, B, C, or X to represent a random variable. For a discrete random variable, we can make what's called a probability distribution. A probability distribution is a representation of every possible outcome of that discrete random variable and the probability associated with each of those outcomes. Now, we could either be given one of these probability distributions in the form of a graph or a table, or we could use some information to create one on our own. Let's look at a couple examples. This first example of a random variable in creating a probability distribution for it involves horse racing. So let's just say that you own a racehorse and you're going to enter that racehorse into 2 races. Now here's what we know. The probability the horse wins the first race is 65%. If the horse wins the first race, the probability it wins the second race is 75%. However, if the horse loses the first race, the probability it wins the second race is 20%. Now, we're going to let X be the random variable, how many races the horse wins. Now, why is this a discrete random variable? Because X is how many races the horse wins. And that is a listable, countable number of values. The horse could win 0 races, the horse could win 1 race, or the horse could win 2 races. 0, 1, and 2 are all listable, countable, and they're numerical. Now, to figure out the probabilities, because remember, probability distribution doesn't just have the list of possible outcomes for X, it also has the probabilities, we're going to need to learn a lot of the tactics that we learned back in the first video over Unit 4, basic probability. Now, the first thing I notice is that these are conditional probabilities, because what happens for that second race all depends on what happens on that first race. Now, to understand conditional probabilities, it's best to make a tree diagram. So let's do that. So first, the race is for race 1, and the horse enters it, and we see that there's a 65% chance the horse wins that race, which means automatically the complement is a 35% chance the horse loses race 1. Now here comes our conditional probabilities that were given to us. If the horse wins race 1, so let's follow that 65%, there's a 75% chance the horse will then go on to win race 2. The complement of that would be a 25% chance that the horse loses race 2 after the horse won race 1. Then the horse could lose race 1, so we're going to follow that 35% branch. Now, we were told that the horse has a 20% chance to win race 2 if it lost race 1. So that would be 20%, and then the complement would be 80% chance that the horse loses race 2 if it already lost race 1. Now, to get to the end of any of these branches, all we have to do is multiply, and as long as we're understanding that these are conditional probabilities, what happens for race 2 depends on race 1, we are certainly allowed to multiply. So let's talk about the top branch where the horse wins 2 races. That's going to be 0.65 for the first race times 0.75 for the second race. Now that's going to give us a total of 0.4875 for the result of 2 wins. Now what about 0? Let's follow that bottom branch. No wins. 0.35 for the first race and then 0.80 for the second race. That's going to give us a total of 0.28. Now the other 2 branches are different. lose the first, win the second, or win the first, lose the second. They are different, which means they can't happen at the same time, but both of them have the same outcome of one win. So to find the probability of one win, we have to calculate each of those branches and add them together. So we have 0.65, win the first, 0.25, lose the second. Or, so now we're going to add the next option, lose the first, 0.35, times win the second, 0.20. Add those options together and we get a grand total of 0.2325 for the probability that the horse wins one race. So now we have a probability distribution for our discrete random variable x. We have our outcomes 0, 1, and 2 and the associated probabilities. Now just note that we do, because this is numerical, we do like to put them in increasing order, smallest at the top and then biggest at the bottom. So we like to go in that order of 0, 1, and 2. For our second example, let's talk about having a game. And when a player plays this game, the player could either get 0, 1, 2, or 3 points on any given play of the game. Now, here is a probability distribution in the form of a graph for this scenario. So across the bottom, we see the outcomes 0, 1, 2, and 3, and then the graph shows us the probabilities for each of those outcomes. So we see the probability of getting 0 points is 10%, 0.1. Probability of getting 1 point is 3%, or excuse me, 20%, 0.2. Probability of getting 2 points is 40%, 0.4. And the probability of getting 3 points is 30%, 0.3. Now, this has a probability distribution already built for you. We already have the outcomes across the bottom and the associated probabilities, so no real work for us to do here. But I can ask you more probability questions. Like, hey, what's the probability that on one play of the game, you get 1 or 3 points? Okay, well, all we have to do is add. We know that the word or means to add. So we're going to take the probability of 1 point, 0.2. We're going to add the probability of 3 points, 0.3, and we get a 50%, 0.5, 50% chance that on one play of the game, the player scores 1 or 3 points. Now, what about our formula for addition where we have to subtract away the overlap? Well, this is mutually exclusive. A player cannot get 1 and 3 points on the same play, so we don't have to worry about subtracting anything away because we're basically subtracting away 0, which does nothing, because these two events, 1 point, 3 point, are mutually exclusive. Here's a third example. Let's say that every year the Cookeville School District has job openings for teachers. And when there's a job opening for a teacher, they have to conduct interviews. Now let's let T represent how many teachers they interview for any one job opening. So let's just say there's a new math teacher and they have a job opening for that new math teacher, so they're gonna have to hire some teachers, and that means they're gonna have to interview some teachers. So how many teachers they interview? Well, here is a probability distribution for the random variable T. Now this is another one that's already done for you. We have all the possibilities for T. They interview 1, 2, 3, 4, 5, or 6 teachers, and then the associated probabilities are underneath them. Nice and simple, you don't have to do any work, it's already created for you. But again, we could ask you some very basic probability questions using those things that we learned in part 1 of the Unit 4 summary review video. For example, what is the probability of at most 3 teachers needing interviewed? Well, you just have to know what at most 3 means. At most 3 means 3 or less. So that would be 3 teachers are interviewed, 2 teachers, or 1 teacher. So all we gotta do is add those 3 probabilities together to get that answer pretty easily, 0.11 plus 0.06 plus 0.03, and that's gonna be a grand total of 0.20. Very simple, so 20% chance that at most 3 teachers are interviewed. What is the probability of interviewing 2 or 4 teachers? Well, 2 teachers, 0.06, or means add, 4 teachers, 0.20, add them together for a 26% chance. Now, why don't I have to subtract anything away? Well, the same thing I just got done mentioning in the previous example. Interviewing 2 teachers and interviewing 4 teachers is mutually exclusive. You can't interview 4 and 2 teachers at the same time. It's going to be one or the other, so you don't have to worry about any overlap. One more question. What is the probability of at least 4 teachers being interviewed? Well, once again, all you have to do is make sure that you know what at least 4 means. At least 4 means 4 or more. So we're going to add together 4, 5, 6 teachers being interviewed. That's 0.2 plus 0.25 plus 0.35. Add them together and you got your answer. It's that simple. So when a probability distribution is given to you, it's pretty nice, it's pretty easy. All you have to do is understand what you're looking at and how to answer some pretty basic probability questions. Now let's go back to the game problem that we looked at in example 2. Now, this is going to be a little bit trickier because let's say that we're going to now play this game twice. We're going to play the game once, and then we're going to play the game again. And now we first have to assume that each play of the game is independent of the next, which means what happens on the first play, whether I get 0, 1, 2, or 3 points, has no impact on what happens on the second play. That's going to be really important. If that wasn't true, I actually couldn't do what I'm about to do. All right, so here's the deal. We're going to create a new random variable, s. S is the sum of the 2 plays of the game. Now, what are the possibilities for s? Well, first off, what we're looking at is the probability distribution for one play of the game. We could score 0, 1, 2, or 3 points for one play of the game. But what about the sum of 2 plays? Well, first we could get 0 points. How would we get 0 points? We'd have to get 0 on the first game and then 0 on the second game. That's a very easy probability to calculate. 0.1 times 0.1, 0.01, we're done. Now, what about the probability of 1 point? Okay, this is where we really have to think about the fact that we're playing the game twice. There's a first play of the game, and then there's a second play of the game. So to get a total of 1 point, we could get a 0 on the first play and then a 1 on the second play. Or we could get a 1 on the first play and a 0 on the second play. Now they both involve a 0 and a 1, but here order matters because there's the first play of the game and the second play of the game. Now the good news is this, getting a 0 and getting a 1, those probabilities don't change. And the order we multiply doesn't matter. So for the first scenario, 0 on the first, that'd be 0.1 times 1 on the second, times that by 0.2. So 0.1 times 0.2. But if we switch that around and we get the 1 first and then the 0, well, multiplication, it's still going to be 0.2 times 0.1. But again, they are different. Ultimately, each scenario is a 0.1 times a 0.2, but there's 2 different scenarios that are distinctly different. So one way we could speed that up is just doing 0.1 times 0.2 and then multiplying by 2 for the 2 different possible ways that can happen. All right, what about getting 2 points? Okay, let's walk through this. We could get a 0 and then a 2, or a 2 and then a 0. Those are distinctly different. Or we could get a 1 and a 1. Now, there's only one way that can happen, 1, 1. We can't switch it around and make it look any different. It's still 1, 1 no matter how you look at it. So we have 3 different scenarios. So for the 0 and the 2, that's 0.1 times 0.4. But there's 2 ways, so I'm going to do 0.1 times 0.4 times 2, because there's 2 scenarios, 0, 2, or 2, 0. Or the other scenario that can only happen one way is 1, 1, and that's 0.2 times 0.2. All right, hopefully by now you're starting to get the hang of this. Let's speed it up a little bit. What about 3 points? Well, we could do 0, 3, 3, 0, or 1, 2, or 2, 1. So we actually have 4 different scenarios there. What about 4 points? Well, we could do 1, 3, or 3, 1, or 2, 2. Okay, 3 different scenarios there. Finding the probabilities is pretty simple. Then we could get 5 points, 2, 3, or 3, 2. 2 different scenarios there. And then finally, we have 6 points. There's only one way that could happen, 3, 3. Again, you can't make that look different. 3, 3, 3, 3 is still 3, 3. So that would be 0.3 times 0.3 for our probability of getting 6 total points. So now we could create our probability distribution here showing all of those possible outcomes, 0, 1, 2, 3, 4, 5, 6 for the sum of 2 plays and the associated probabilities. But you just have to be very careful calculating all those probabilities. Now, one thing I like to do at the very end is add them all together to ensure that you are going to get a total sum of 1. All probability distributions for a discrete random variable should have all the probabilities adding up to 1. So in total, we find the probability of getting a 0 points is 0.01. The probability of getting 1 point is 0.04. The probability of getting 2 points is 0.12. The probability of getting 3 points is 0.22. The probability of getting 4 points is 0.28. The probability of getting 5 points is 0.24. And the probability of getting 6 points is 0.09. And if you add all this together, guess what? You get 1, or as a percentage, 100%, which means we did our work correct. So problems where you have to take a probability distribution and then repeat it sometimes can be a little bit tricky. So make sure you take your time, write out everything that can happen, and make sure you understand if you change the order, how it does matter when there's a first play and a second play. And then creating the probability distribution isn't that bad. Now, since a random variable is numerical, an interpretation of a probability distribution can be made that it gives us information about the shape, the center, and the spread. Now let's talk about shape first, because if you have a probability distribution, talking about the shape of it is actually really, really simple. Now, if you have a graph, all you gotta do is look at it. Does it look skewed left? Does it look skewed right? Does it look symmetrical? Does it look bimodal? Or if you have just the probability distribution table, well then you sometimes either could make a quick graph or just kind of visualize one. Let's actually take a look at the problem we saw earlier for how many teachers they're going to interview for any one job opening. So if we look here, we notice that the probabilities increase as we move from left to right. So the probabilities of 1, 2, 3 are kind of lower, where the probabilities of 5 and 6 are kind of higher. So just visualize that would be a skewed left graph. The outcomes on the right are way more likely than the outcomes on the left, and if we were to make a histogram of that, we would see a skewed left graph. So we could easily talk about shape when we're talking about a probability distribution. Whereas if the outcomes on the far left and the outcomes on the far right were both low and the outcomes in the middle were much higher, well then that would be roughly mound-shaped and symmetric or unimodal. So all those things we learned way back in Unit 1 when it comes to describing the shape, we could use here as well for probability distributions. Next, we can find the mean, which is referred to as the expected value of a random variable, and the standard deviation of a random variable to help us describe the center and the spread of a probability distribution. Let's start off talking about the mean. The mean is also known as the expected value. It's what we expect the outcome of the random variable to be in the long run after many trials or many passings of this random process of this random variable. Now, to find the expected value or the mean, it's actually not that complicated. All you have to do is take each outcome times its probability and then add all of those together. So we could do that by hand, outcome times probability plus outcome times its probability plus outcome times its probability, ... Or we also have this formula given to us on the AP Stats formula sheet, which tells us that the mean, mu. Now remember why we're using that symbol mu. Because here we're talking about the long run, which is essentially infinite, right? We're talking about the population or parameter here. So we're saying that the mean, the expected value for this random variable x in the long run is, well, here it is. It's using this formula. So that giant looking E is sigma, so we're going to add together each individual outcome times that individual outcome's probability. Once we multiply and add all those together, we'll get our expected value. Now the standard deviation formula is a little bit trickier. First, the standard deviation symbol is sigma. So the standard deviation of our random variable x equals, all right, let me walk you through this here because it's going to be a little bit trickier than the mean. But what you do is you take each individual outcome minus the mean, which you have to calculate first, square that difference, multiply by the probability of that individual. Now, once you get done doing all that, outcome minus the mean squared times the probability, and you add all those together, you get what we call variance. Then you square root all of that variance to get what we call standard deviation. Now I know those two formulas for the mean and the standard deviation are a little bit tricky and a little bit overwhelming, but don't let that concern you. In a couple moments, I'm actually going to show you how you could use your TI-84 calculator to find both of them with very little work. But perhaps what's most important than the formulas is actually understanding what these two values represent. The mean is the expected value of the random variable in the long run. So if we were to repeat the random variable many times, it's the expected or the average value we would expect in the long run. For example, if we said, hey, there's a new job opening, how many teachers do you expect to have to interview? Well, that's what the mean of the random variable would be. Now, this purpose of the standard deviation is to give us an idea of the precision of that expected value. High values of the standard deviation relative to the expected value tell us that the expected value is, well, very imprecise. Whereas if we had low values of the standard deviation relative to the expected values, it would give us an opposite implication. Now, the standard deviation gives an idea of a plus or minus range for the expected variable. So we can actually kind of find an interval for what outcomes of the random variable are most likely to occur by taking the mean, going up and going down one standard deviation. Now, let's quickly talk about how we could use that TI-84 calculator to find the mean and standard deviation of a discrete random variable for us. Now, the first thing we're going to need to have our calculator find the mean and standard deviation for us is we need the probability distribution. Again, we're going to need each individual outcome of the random variable and its associated probability. Let's use the teacher job interview example for this particular problem. So the first thing we have to do is put this data into our calculator. So we're going to hit Stat, Edit. Now this is where we can actually enter in lists of information into our calculator. So in list 1, we're going to put the outcomes. 1, 2, 3, 4, 5, 6. So list 1 is the outcomes for the random variable. And then in list 2, we're going to put the associated probabilities. Just make sure that the probabilities are next to the correct outcome. So next to 1, we need 0.03. Next to 2, we need 0.06. Then 0.11, 0.20, 0.25, and 0.35. That's it. That's actually all the hard work you have to do. Now all you're going to do is hit Stat, slide over to Calculate in the middle, and then select one variable stats at the very, very top. Now it's going to ask you for two things here. The first thing it's going to say, where is the list of data? There, we're going to make sure we put list 1. So second, number 1, if it's not already there for you already. Now that's where it's going to look for the possible outcomes of a random variable. But then underneath it says frequency list. Now we need to tell it that the outcomes in list 1 are not equally likely. They have associated probabilities or frequencies for them. So in the frequency list line, we're going to need to put list 2 where our probabilities are, so second, number 2. Then all you got to do is hit enter and everything is there for you. The very, very top is the mean. Now the only thing I don't like is it uses X bar. It's actually not X bar because this is not a sample. This is all, many, 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 right? This is a lot number, a large number of jobs. So it's job opening after job opening after job opening, and we're going to find the mean or the expected number of teachers that would need to be interviewed. Now at the very top, we see that value. Now down below, we see sigma. Sigma is the standard deviation, and I like that symbol because that is sigma, the standard deviation. So we see that on average, the expected value is 4.63 teachers for any one job opening. So if somebody said, hey, how many teachers do you expect to interview for that new math job? Well, 4.63. But sometimes it's a little bit more, sometimes a little bit less. The standard deviation would be 1.37 teachers. Understanding what those two numbers means, again, is super important. So oftentimes on the AP Stats test, they're going to ask you to find those values and interpret them. So you'd say something like this. In the long run, if the school district were to have many job openings, they would expect to interview 4.63 teachers for each job opening, but that value could easily vary by 1.37 teachers. All right, that's how easy it is to use your calculator to find the mean and standard deviation of a discrete random variable. All right, the last topic I want to talk about when it comes to random variables is transforming and combining random variables. Now to explain these two topics, we're going to use the following example. Let's say that Gavin has a small shop that sells sweatshirts and sweatpants. Now, he knows that the random variable S is the number of sweatshirts he sells per day, and P is the random variable how many sweatpants he sells per day. And let's just be told that we already figured it all out, and we know that the mean for S, the number of sweatshirts he sells, is 15.7 sweatshirts per day, but some days he has more, some days he sells less, so the standard deviation is 2.5 sweatshirts. And for P, the number of sweatpants he's going to sell per day, we have a mean of 10.6 sweatpants per day, but again, some days he sells more, some days he sells less. There's a standard deviation of 1.8 sweatpants. Now, when it comes to transforming a random variable, here we're mostly talking about converting the random variable from one unit to another. Now, all you have to remember is a couple things we actually talked about way back in Unit 1. First, when you are multiplying a random variable by a constant, both the mean and the standard deviation will get multiplied by that same constant. Okay, that's pretty easy. However, when we're adding or subtracting a constant to a random variable, only the mean would get added or subtracted by that constant. The standard deviation does not get affected at all by the addition or subtraction of a constant. If you can remember those simple rules, transforming from one unit to another is quite easy. For example, let's just say that Gavin sells his sweatshirts for $30 a piece. And we want to transform our random variable S, the number of sweatshirts he sells per day, to R, the revenue for how much money he brings in per day from selling sweatshirts. Well, it's as simple as multiplying. For the mean, all we're going to do is take the 15.7 sweatshirts he sells per day, multiply it by 30 to get $471 for the expected long-run revenue per day from selling sweatshirts. And standard deviation also gets affected by multiplication of a constant. So we're going to take the 2.5 and we're going to multiply that by 30 to get $75. So in the long run, on average, for the random variable R, Gavin expects to have a total revenue of $471 per day from selling sweatshirts, but some days he sells more and some days he sells less, so the revenue is going to deviate by $75. Now let's transform S, the number of sweatshirts Gavin sells, to one more random variable we'll call P. This is the profit. So the profit is $30 for each sweatshirt, but minus $40 in general as an expense. So here, let's first start off with the mean. Again, we sell an average of 15-point sweatshirts per day, so we're going to multiply that by 30, but then we got to subtract 40, and subtraction does affect mean. So once we do 30 times 15.7 minus the $40 in expenses, we get $431 in profit. Now what about the standard deviation? Well, remember, addition and subtraction do not affect standard deviation at all. So the standard deviation is going to be 30 times the 2.5, because multiplication affects standard deviation, but that's it. We're not going to add, we're not going to subtract 40, nothing. So it's just 30 times 2.5, so right back to $75. So the expected profit per day from selling sweatshirts is $431 with a standard deviation of 75. If you can remember those simple rules when it comes to transforming random variables, it's really, really simple. Now, what about combining random variables, which means that we take two or more random variables and kind of combine them together, or we could take one random variable and just repeat it multiple times. Now, this can be a little bit tricky. So to explain the idea of combining random variables, we have to talk about a couple ground rules first. The first rule is that if you're going to combine random variables together or repeat one random variable multiple times, each outcome must be independent of the next. So what happens to one random variable cannot impact the next random variable if you're going to combine them. Keep that in mind. Next up, if you're going to combine random variables, how does that impact the mean? Well, very simply actually, you just combine the means together. Even if you're looking at the difference between two random variables, you are allowed to subtract means. So when it comes to finding the mean of combining random variables, you just add or you subtract as many times as necessary. Really, really simple concept. But here's where it gets a little bit tricky working with standard deviation. I'm going to say this 2 times. You are not allowed to combine or add standard deviations together. One more time for clarity. You are not allowed to add or combine standard deviations together. But what you are allowed to add or combine is variance. Now, how do you get variance? All you have to do is take your standard deviation and square it. I don't even care if you actually find the value of the variance. If you just take your standard deviation, let's say it's 2.5, just put a little square above it. Putting that little square above it, 2.5 squared, now we're talking about variance instead of standard deviation. And we are allowed to combine variance. Now, we're not allowed to ever subtract variance. That's because whether you're looking at the sum or the difference between two random variables, the fact is you're looking at two of them, so the standard deviation, the variance, always builds. So you're always going to add variance. So all you have to do is to get your standard deviation is this. You have to first convert to variance, then add all of your variance together. Once you have your total combined variance, then you're going to put a square root around all of it to get back to standard deviation. Little bit tricky to hear me talk about it. It's going to be really easy to understand once we take a look at a couple of examples. Let's let the random variable T be the total number of sweatshirts and sweatpants that Gavin sells per day. All right, let's find the mean and standard deviation for T. All right, really simple. For the mean, we're simply going to add the means together because you are allowed to add means, no problem. So it's 15.7 total sweatshirts plus 10.6 total sweatpants. Add them together to get an expected value for T of 26.3 total sweats, okay? Very simple, easy to do. But what about the standard deviation? You're not allowed to add them. What we're going to do is add the variance. So the variance for sweatshirts is 2.5 squared. Plus the variance for sweatpants is 1.8 squared. Adding all that together is our total variance. Square root all of that total variance to get back to our final standard deviation for T, 3.08. Nice and simple, not too difficult once you actually see me doing it. Now what about the difference? If we said, all right, let's introduce another random variable, D, the difference between the number of sweatshirts and sweatpants that Gavin sells. Well, subtraction. All you gotta do is subtract the means. That's really simple. 15.7 is how many sweatshirts minus 10.6 how many sweatpants. So we get an expected difference or a mean difference of 5.1. Really, really simple. But what about the standard deviation? Well, you're not allowed to add nor are you allowed to subtract standard deviation. We always add variance. So we're going to take the 2.5 squared, that's the variance for the sweatpants, plus, even though we're looking at the difference, we still add because you're still looking at two things. So variance always builds. So we're going to add the 1.8 squared, that's the variance for the sweatpants, square root all that variance to get 3.08 as the standard deviation for the difference as well. Now let's look at repeating a random variable multiple times. So let's introduce another random variable, let's call it W, the total number of sweatshirts that Gavin sells in a week. So remember, we know that 15.7 and 2.5 are the mean standard deviation for one day, but we have 7 days now. So you see how we're repeating this random variable. So the first thing we're going to do is we're going to say, all right, well, Monday 15.7, Tuesday 15.7, all the way to Sunday 15.7. So we could add 15.7 7 times, or we could do what's very logical. We could use multiplication, because remember, multiplication is repeated addition. So 15.7 sweatshirts for 7 days, 15.7 times 7 is 109.9 as the expected or the mean value for W, how many sweatshirts he sells in a week. All right, what about the standard deviation? Well, once again, we're not allowed to add. So we can't add the we can't add the standard deviation for each day, but we can add the variance for each day. So each day's variance is 2.5 squared. So the variance for Monday is 2.5 squared, Tuesday 2.5 squared, Wednesday 2.5 squared. So we have 2.5 squared for 7 days. So we have 2.5 squared, that's our variance for a single day, times 7 for 7 days. Put a giant square root around all of that because we have to take the square root of all of our variance to get back to our standard deviation. So we get 6.61 as the standard deviation for W, the number of sweatshirts that Gavin sells in a week. So after we did all this work, we know that in a week, we expect Gavin to sell 100.9 sweatshirts in the long run, which means if we looked at many weeks, in the long run, we'd expect 109.9 sweatshirts per week, but some weeks he's gonna sell more, some weeks he's gonna sell less, so the standard deviation is 6.61. Little bit confusing there at the end with combining random variables, but hopefully you understand those very simple rules. First, what happens on one day to the next day, what happens with sweatshirts, what happens with sweatpants have to be independent. And then we have to remember that you are allowed to add, you are allowed to subtract means all you want. But when it comes to standard deviation, I can't emphasize enough, you cannot add or subtract standard deviations. You can only add variance. And then you got to convert that variance by square rooting it to get back to standard deviation. Overall, it's not too difficult, but you have to be very diligent in taking your time and understanding how this works. All right, that's it for random variables. Hopefully you understood it and hopefully it made sense. All right, remember this was just the end of part 2 of the Unit 4 summary review video. Please don't forget to check out part 3 that covers the binomial and geometric distributions. Can't wait to see it in that video.